Imagine, as you walk into a traditional Chinese medicine clinic filled with the aroma of herbs, the doctor reaches out, gently resting their fingertips on your wrist. This is called taking the pulse, although this might sound very mystical to many. From the perspective of sensing technology, this is actually an extremely low bandwidth data collection process. The doctor tries to feel through skin, fat, and multiple layers of connective tissue to sense the faint pressure fluctuations of the subcutaneous artery and infer the operating status of unseen organs deep within your body, such as the heart, liver, or even the endocrine system. This is actually the biggest dilemma currently facing human brain-computer interfaces. The current mainstream electroencephalography (EEG) technology is like taking a pulse through a thick down jacket, although it seems safe and perfect, requiring no surgery. Just attaching electrodes to the scalp. The signals must pass through the cerebral cortex, the dura mater, the thick skull, and finally the skin. During this process, the weak electrical signals generated by neurons are severely refracted, attenuated, and scattered. What the doctor or computer receives is just a bunch of blurry noise waveforms. The communication bandwidth is extremely low. At most, you can tell if the person is sleeping, zoning out, or agitated, trying to accurately decode thoughts with it, or even transfer knowledge, like in The Matrix. It's simply a technological fantasy, since taking a pulse through skin and flesh is unclear. The scientific community's approach over the past decades has been very direct. Just place the stethoscope directly inside the brain. This brings us to a relic from the Paleolithic era of BCI, the Utah ray. This technology is hardcore. It's like a miniature bed of nails, covered with rigid silicon probes. During surgery, doctors use a pneumatic device to violently hammer this bed of nails into your cerebral cortex. Although it can hear clearly, the brain is not a fixed piece of plaster. It's actually like a large, jiggling piece of jelly inside your skull. When you breathe, when your heart beats, when you turn your head, brain tissue is constantly shifting at the micrometer level. At this point, those rigid silicon probes act like miniature sharp knives, repeatedly slicing through the brain tissue. This triggers a severe immune response in the brain. Glial cells, like a scab forming over a wound, will grow thick scar tissue to completely envelop the probes, attempting to isolate the foreign objects. In less than a few months, the signal is cut off again due to this biological isolation layer. This is why implantable brain-computer interfaces have been studied for 30 years, but have never been able to leave the lab and become consumer products. This is the fundamental contradiction that Elon Musk and his Neuralink aim to challenge. We need extreme signal quality, but we cannot harm the soft brain. The core logic proposed by Neuralink involves only one key transformation: shifting from rigid probes to flexible threads. They developed a microscopic material never before seen by humanity. It's a polymer fiber thinner than a human hair and softer than plastic wrapping. Each thread distributes 32 miniature electrodes, and one set of connections has 1,024 channels. This is no longer taking a pulse. This is directly plugging 10,000 optical fibers into the communication backbone of neurons. These flexible threads can be formed synchronously with the brain's jiggling, drastically reducing the immune response. In theory, it allows the brain-computer interface to work stably in the brain for decades. But you might ask, if flexible threads are so good, why didn't previous scientists use them? This brings us to the cruelest part of engineering, because human hands simply cannot do it. Imagine, you have to precisely insert a thread thinner than a hair and as soft as cooked noodles into a living brain. And most fatally, the surface of the brain is covered with microvessels. If your probe pierces a blood vessel upon entry, internal brain bleeding will immediately cause neuron death and inflammation, turning the expensive equipment into a piece of scrap metal. Past solutions were an engineer's nightmare, relying on manual operation under a microscope. It had a failure rate so high it caused researchers to despair. This is also why Neuralink chose an extremely crazy path. They didn't let humans do it, but instead built an automated surgical sewing robot. This robot is the unsung hero of this entire technological revolution. It is equipped with multi-angle cameras and structured light sensors, using computer vision to track the brain's pulsation in real time. When preparing to implant, the algorithm automatically plans the path, precisely avoiding every microvessel on the brain's surface. Then, an extremely fine steel needle hooks the flexible thread, and at a speed of several threads per second, like a sewing machine, swiftly and elegantly delivers the electrodes to the predetermined depth. This is not medical equipment. This is the unsealing of precision manufacturing, showcasing the purest violent aesthetics of mechanical engineering. However, you think it's over once the implantation is done? No, this is just the beginning of the challenge. The true ultimate boss is hidden in signal processing and energy management. When you have 1,024 electrodes simultaneously collecting data, the raw data generated per second is massive. If you wanted to wire them out using traditional cables on your skull, you would have to plug in a bundle of cables as thick as an adult's arm. This is obviously unrealistic. Therefore, Neuralink had to achieve fully wireless transmission. But performing wireless transmission inside the closed environment of the brain comes with a physical limit: heat dissipation. The brain is the human body's most delicate organ and is extremely sensitive to temperature. If your processing chip heats up slightly while operating, a temperature rise of more than 1 degree will induce nerve cell necrosis. Processing high-frequency signals from over 1,000 channels in a tiny volume, while simultaneously handling wireless transmission, makes thermal power management a nightmare. Neuralink's approach is to take an extreme, the path of bottom-level self-research. They do not use any off-the-shelf processors on the market, but instead developed a dedicated custom ASIC chip. This chip is responsible for completing the amplification of analog signals locally, as well as filtering, digitizing, and compressing them. They controlled the power consumption down to the microwatt level, and even developed an inductive charging technology that penetrates the skin. This means that you only need to sleep at night while wearing a specially made wireless charging pillow to fully charge the device inside your brain. Having said that, we must step back from the technical details and look at the broader picture. Currently, Neuralink's first human clinical trial patient, Nolan Arbaugh, has already demonstrated shocking results. This quadriplegic young man can now play Civilization and Mario Kart purely with his mind, and even joke that he's using aimbots in his brain. For people with disabilities, this is not just a technological breakthrough, but a regaining of dignity. But Elon Musk's goal obviously goes beyond this. He has repeatedly emphasized that humans need BCs. In order not to be eliminated in the future AI era, he believes humans' current output bandwidth is too slow. You might have 10,000 ideas in your head, but you can only rely on your two thumbs to type text on a screen or communicate via a throat that can only spit out a few words per second. This extremely low communication efficiency makes humans look like slow-motion antiques in front of AI. Neuralink's ultimate vision is to expand human intelligence. If we could directly read the spikes of neurons and utilize neuroplasticity to let the brain get used to collaborating with external chips, then downloading knowledge or using cloud computing to assist thinking will no longer be science fiction. Of course, this path is full of huge controversies. Besides the thermal power and biocompatibility mentioned earlier, there are deeper ethical issues. If a person's memories can be read, does privacy still exist? If the rich can install BC is first to enhance their intelligence, Will that create the most massive intelligence class divided in human history? Even in engineering, we still have many unsolved problems. For example, brain neurons will age, and the relative position between the threads and neurons will also change over time. How to make algorithms automatically adapt to this neural drift? To keep decoding accuracy consistent, this requires machine learning. To make more adaptive adjustments at the base level, we are standing at a singularity. The essence of engineering is to find that optimal solution amidst countless constraints. Neuralink did not invent neuroscience out of thin air. What it did was to utilize contemporary cutting-edge precision machinery, semiconductor manufacturing, and software algorithms to forcibly push a 30-year-old scientific concept to the brink of commercial mass production. This is a turning point from traditional Chinese medicine-style vague observation to fiber-to-the-home style precise communication. When we look back, we might find that Neuralink's greatest achievement isn't that sewing robot, nor is it that ASIC chips, but rather that it broke the seemingly insurmountable boundary between biological organisms and machines. It tells us that although the brain is complex, it still follows the laws of physics. As long as we can unlock the seal on bandwidth, the next chapter of human evolution will be written by ourselves. Seeing this, do you think humanity is truly ready to enter this era of digitized brains? If you had the chance, would you be willing to implant such a chip in your brain?